Hello, this is Nasnianevsky, and so we're up to section 5.4. We're going through this monoidal category theory book. Okay, so this section is like a breather because section 5.3 we went through the definition of a monoidal category and a few variations of it, and we saw a lot of examples. So this section is like okay, what's all this coherence theory all about? What's all this stuff about worrying about how these natural transformations come about or get along with each other, cohere with each other? So that's what we're going to spend today talking about. It's a few different topics that come up, and it's kind of interesting. Actually, it's very interesting. Okay, so what I want to do is go back to classical arithmetic, okay? Numbers and addition and multiplication. And one of the things we saw, one of the things that you see in, I don't know, elementary school is that if you have three numbers and you have an associate, then if you have three numbers, then, and you have some operation between these numbers, okay, then we have the following rule. Okay, ready? If these two are associative, if this is true for all A, B, and C, okay, then that's an axiom. If you assume this axiom is true, then what you have is for all numbers and for all parenthetizations. Okay, any parenthesization okay, I don't even know if that's legitimate. Well, it's clearly not. Okay, any parenthesization whatever value the numbers will give you, either here or here, they'll be equal. Okay, so that's the whole purpose of this associativity axiom. It says if this is true for 3, then given any parenthesization, given any association, okay, it's going to have a value, and it's going to be the same value no matter what the parenthesization is. And so, in other words, if you have two different parenthesizations, you will still have the same value. Okay, so that's something that's true for arithmetic addition. It's true for multiplication. It's not true for subtraction, and it's not true for division because those do not satisfy this axiom. Similarly, there's another axiom about commutativity. A tensor B tensor. You know what? Let's leave out for a second. Let's leave out the tensor. Okay, let's leave it in. Sorry. Okay, A tensor B and B tensor A. If this is true, then again you can have Then for any grouping, let's say E tensor A tensor G tensor B tensor D tensor F A B, we need a C, okay, A B C D E F G, okay, or C tensor B tensor A tensor F tensor G A B C D tensor D tensor E. Any ordering, no matter what, they'll be equal. Okay, so again, if this axiom is true, then it doesn't matter how you order the elements. You can order them this way, you can order them this way. The value you're going to get at the end is going to be equal. Okay, so that's the whole idea about basic algebra. Great. Now, what does that, and this is true for, again, multiplication and addition. It's false for subtraction and division. Okay, you don't have that axiom. Okay, great. What does this have to do with coherence theory? And the idea is somehow that was algebra. This is more higher dimensional algebra. And it goes as follows. Okay, you have some operation A on a category, tensor B, tensor C. Okay, there's an isomorphism A, tensor B, tensor C, like this. Okay. We're now not talking about them being equal. We're talking about there being an isomorphism. Okay, great. Now, I have a category. And I have a large thing like this. Okay, shouldn't have erased it last time. Okay, and one is associated this way, and one is associated this way. Or something like that. Just two different associations. Okay? And the question is as follows. There's one isomorphism from here to here. Question, how many isomorphisms are there from here to there? Okay? And the answer is, and this is what coherence theory is all about, the answer is that if you assume that pentagon commutes, then for any association and any other association, let's just see what this says. This says A, B, C, D. This says A, B, C, D. Okay. There's three other associations, but if this commutes, then that means there's a single map from here to there. Then there'll be a single map between any one of these. Okay, and the single map, of course, there might be other maps, whatever, but a single map made out of these alphas. So that's the analogy. Namely, let's go back. In arithmetic, if the axiom A tensor B tensor C is equal to A tensor B tensor C is satisfied, then you're going to have a unique value for any reassociation. Okay? That's classical arithmetic. Now here, if this axiom is satisfied, namely there's a unique morphism from here, then there'll be a unique morphism between any two reassociations. Okay, so that's a statement. I'd like to prove that statement. We're not going to prove it today, but I'd like to give you the intuition behind the proof. The intuition behind the proof is very nice. I'm sorry, the intuition is much better than the proof. The proof is technical, etc., but the intuition is as follows. Okay, so let's go through it. One object, you have one object. There's nothing you do. Two objects, you can do A tensor B. There's nothing interesting. Three objects, you could have like this. Let's leave out, there's a line in between them. Let's leave out the tensors for the minute. That's one object, two objects, three objects. What about for four objects? Well, for four objects, you have the pentagon, the Stashef-McLean pentagon coherence condition. Okay. Question, what about, so this is one for one object, two objects, for three objects, for four objects, what about for five objects? Okay, and so the answer is, for five objects, I'm sorry, I'm not going to redraw this, that's for sure. This is what it looks like. Okay, it's a ball. It's a sphere. I'm sorry, it's a sphere that looks like this. Okay, I don't know if you can see it or you can't see it. Doesn't matter. It's on page 257 of the book. The main point of this, okay, and that's for 5 objects. For 6 objects, it's too hard to show. Okay, it's too hard to show. But the point is, for 5 objects, it's a type of sphere. Okay. Now, in the picture on page 257, 256, I show you what the sphere looks like. But here, in this picture on page 257, I open up this sphere and I show you each and every one of the associations and each and every of the alphas, how they look. The main point is what this sphere is made of. Okay, it's a sphere made of different things, namely, it's got boxes and it's got pentagons in them. Okay, and you can see them very clearly here. Box, pentagon, pentagon, pentagon. Okay, lots of pentagon, so I think it's 3 pentagons here. The shape is made of 14 vertices, 21 arrows, which form 3 squares and 6 pentagons. Okay, great. How does that help us? Well, the squares all correspond to the fact that the alpha is natural. So, what does that mean? That's a little square. So that's an alpha, that's an alpha, that's also an alpha. There's 2 different instances of that alpha. So that's a square. So we're assuming that our alpha is a natural transformation. We don't have any other types of transformations between functors other than natural. We haven't discussed any, okay? And the pentagons are examples of this axiom, are instances of this axiom. Main point. If you assume that alpha is natural, namely the squares commute, and you assume that the axiom, the pentagon axiom, commutes, then any single path between 2 objects in this category, okay, and again, they're all isomorphisms because alpha is isomorphisms and you have identities, any two paths will equal, and in fact there'll only be 1 path between them. So that's the intuition behind this thing. Okay, so you're not getting that the 2 associations are equal. That's not true. That's true in lower dimensional algebra. Here, you're not getting them that they're equal. You're getting that there's a unique path between them. And I told you, in category theory, we have this obsession about uniqueness of paths. Okay, isomorphisms, unique up to isomorphisms. Okay, and this explains why it is. Okay, so great. That helps you for 5. What about 6, 7, 8, 9, 10? We had A, B, C, D, E, F, G. G is 7. What about that? Okay, and the answer is for all of them, and this is not proven here, but for all of them, for any n, okay, so notice what you have here. Here you have a circle, here you have a sphere. For 6, you're going to have a higher dimensional sphere. And so basically, for any n, you're going to have an n minus 2 sphere. Okay, and they're all going to be made out of, you ready? Squares, which are naturalities, and pentagons. And the main theorem is, if you assume the squares are commute because of naturality, and you assume the pentagon commutes out of the pentagon condition, it's an axiom, then the entire sphere commutes. So this is not only true for 1, 2, 3, 4, 5, 5, you can see it, it's true for 6, 7, 8, for all of them. Okay, and that's extremely interesting. So it's a geometric proof of this thing. Another way to think of it is as follows, and I like to think of it this way. What it means for this to commute is that this is not a circle, but it's a filled in flat plane. And what it means for this to commute is not that it's not a sphere, but it's a filled-in black ball. I'm sorry, it's a filled-in ball. Okay, it's not a sphere. It's not just the cover of the sphere of a ball. It's a filled in. As long as you assume it's commutes, or as long as it commutes because of these reasons, etc., then think of this. Think of this not commuting. Then you have one path this way and one path this way. They're not the same. But if it does commute, okay, then this path is really the same as this path. You can change one path to the other. Same thing here. If this didn't commute, then there would be two different paths from here to here. But since they're filled in, it does commute. Same thing here. For n, you have an n minus 2 sphere. It commutes. Okay, great. Okay, question. Okay, sorry. Just want to say, commutativity is much more complicated. So we're not dealing right now with commutativity. We'll deal with it soon, but we're not dealing with it right now. Okay, but associativity has that thing. So the axiom goes along. Okay, and again, this explains why it's called higher dimensional algebra. Algebra deals with operations. Higher dimensional algebra, or coherence theory, deals with natural transformations between operations. Okay, so think of those two different ways of associating three elements. Those are two different operations. You have a natural transformation between them. You want to know what the relationship is, not between the operations, but not amongst the operations, but amongst the morphisms between the operations. Okay, now a way to talk about this is with something called an associahedron. Okay, from the word polyhedron, which means many parts of a shape, okay, and instead of you have the word associahedron, so you're dealing with all the different associations. Okay, so put them all together, you have one associahedron and many associahedra. Okay, that's a plural of associahedron. So you have A of 1, A of 2, A of 3, A of 4, A of 5. Okay, A of 1 is a dot. A of 2 is a dot because there's only one way of associating one element. There's only one way of associating two elements. Okay, A of 3 is a line. Okay, now an isomorphism. The main point is these are shapes. You can think of them as finite categories. Okay, and in some sense they're what's called free categories, but that's fine. Okay, the A of 4 is the pentagon shape. Okay, again, all these are isomorphisms, so you might as well think of them as just straight lines. Okay, and the A of 5 is like this. That thing that's made out of three squares and 6 pentagons, right? And more. There's more. I can't draw them more. Some books try to draw a 6 or something like that. Okay. Now, question: how many vertices do these have? So this is a famous formula, and it's called the Catalan Numbers. Okay, Catalan Numbers. Okay, and it goes like this. This has 1, 1, 2, 5, 14. 1, 1, 2, 5, 14. Hold on. Okay. The next one, which we don't draw, has 42. The next one has 132. The next one has 429. Dot, 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 dot. Okay? So a hell of a lot. Okay? And the formula is as follows. C of n minus 1 is equal to 2 of n minus 1, choose n minus 1, divided by n. Okay? That's called the Catalan Numbers. Okay? They show up in a lot of places in combinatorics. Okay, and at the end of this section, at the end of 5.4, I actually prove that the number, if you have n letters, the number of legitimate kosher parenthetizations is the Catalan number. Okay, the main point is it's exponential. It's exponentially large. So that's an interesting thing. We're proving something about an exponentially large number of numbers, and we're showing that between those exponentially large number of things, there's exactly one morphism that goes between them that is made up out of these Associahedra, associators, etc. Okay, so that's called the Associahedra. And again, we prove it later on. Okay, next, we're not only interested in associations, but we're also interested in Permutahedra. You spell it the way you want. In the book, I spell it right. Okay, or Permutahedra, singular, Permutahedron, and Permutahedra. Okay, so for one letter, there's only one thing to do. For two letters, you have AB and you have BA, and there's a line in between them. For three letters, you have a little bit more complicated. So let's do it for three letters. Okay, it goes like this. A, B, C. I'm leaving out parentheses, and I'm leaving out the tensor product. A, C, B, C, A, B. Okay, that goes there, that goes there, that goes there. B, A, C, B, C, A, C, B, A. Okay, so this is identity tensor gamma, AB, BA. Okay, ABC, BAC. Okay, here this is gamma tensor identity. This is ABC, ACB. So this is identity tensor gamma. This is ACB, CAB. So this is gamma tensor identity. BAC, BCA. This is identity tensor AC, CA. AC, CA, gamma. Okay. BCA, CBA. This is gamma tensor identity. Okay. By the way, notice what we're doing here. You can think of this as, you ready? Keep it identity tensor that. Now, this tensor that. Now, this tensor that. Okay, that's equal to, let's do this, dump, bump, bump. This is dump, bump, bump. This is dump, bump, bump. Okay, let's just make sure it works. 1 goes to 3, 1 goes to 3. 2 goes to 2, 2 goes to 2. 3 goes to 1, 3 goes to 1. Okay, but this was one of those rules about the symmetry groups that we had, the generators of the symmetry groups that we had. So we went something like this: SI, SI plus 1, SI equals SI plus 1, SI, SI plus 1, something like that. Okay, that's the same type of rule. Maybe these were lowercase. Okay, great. Hold on. So we saw those before. Now, question, to what extent does this commute? Okay, and the answer is this commutes because this changes the B. So this is gamma, AC, AC. This is going to be AC, comma, B. And this, CAB, BCA. Okay, so this is CAB. This is gamma of CA, comma B. Okay. In our definition, we had those triangle identities. We had those two triangle identities. Let's remember, last section we had those two hexagon things, coherence conditions, but we said if you're assuming associativity, if you're strictly associative, it goes down to two triangle identities. That's exactly those two triangle identities. Okay, and then here, that's a naturality square. That's a naturality square of gamma. Okay, so that's for 3. That's the shape that you have for 3. Okay, of these Permutahedra. Okay, what about 4? Well, 4 is a little bit hard to draw, and so we don't draw them. Okay, and 5 and 6 and 7. Okay, and we look for, we can't draw these, but we can look for different properties that these things have. Okay, now the coherence condition is not about uniqueness here. When we talk about associativity, it's about uniqueness. Here it's a little bit more subtle, and we're going to have to deal with it, and we will deal with it in chapter 6. Great. Let's go further. Okay. So one thing we could talk about is associativity. Another thing we could talk about is commutativity. And another thing we could talk about is associativity and commutativity. So this is called the Permuta-Associahedra. Something like that. Associahedra. Okay. Permutations and associations. Okay, and we can look at these types of shapes or these types of categories. Okay, and it goes as follows. For one letter, there's just a dot. Let's call it A. For two letters, there's just AB. Okay, but there's also BA. And so there's an isomorphism. For 3, already here, you're going to have a lot more. Okay, how much are you going to have? Okay, I'm sorry, I left out something. In the Permutahedra, okay, how many objects do you have for the nth element? Well, very simple. N factorial. Okay, you have n letters, okay, and you want to know how many different ways of permutations there are, and there are isomorphisms between those permutations. But the answer is n factorial. Great. For the Permuta-Associahedra, we not only have bracketing, but we also have permutations. Okay? And even for A3, it's too hard to draw. I did draw it in the book, and it goes right over there. It's on page 260. It's got, well, let's just see how many things it has for 3, okay? So there are 6 ways of permuting 3 elements, okay? But each way has, for 3 elements, for each one of them, you have 2 associations. So you're gonna have 12 things. So for 12 objects. So this shape in the Permuta-Associahedra has 12 different objects. And what it is, again, something very similar to what we saw before, but in some sense expanded because there's 2 of them. And so this corresponds to 1 hexagon. I'm sorry, these 2 correspond to hexagons. This is a naturality condition. Great. These are called, the Associahedra are called A1, A2, A3, These are called Permutahedra, are called P1, P2, P3, P4. These are called PA1, PA2, PA3, etc., etc. How many objects does this have? Very simple. There are 3 factorial permutations, okay? times 2, because there's 2 ways of associating 3 elements. Very nice. Okay, great. How about for n elements? How many objects are there in the Permuta-Associahedra? And the answer is n factorial times c of n minus 1. Catalan number minus 1. And so it goes to like this. For here, there's 1 element, there's 1 object. Here, there's 2 objects. Here, there's 12 objects. And already for 4, there's 120. For 4, there's 120. Okay? And the next one is 1680. So a little bit hard to draw. Okay? But you have to keep these all in mind. Okay, now let me just foreshadow a little. These Associahedra, Permutahedra, and Permuta-Associahedra, they all correspond to something we're going to call later on in chapter 8, we're going to call them their operads. There are examples of operads. Operads are ways of talking about different functions. A very general definition of what an operad is, but each one of those are ways of describing different functions, and they come together and they form something called an operad. So that's very nice. Let me just give you another thing. Modern physics, and this is not in the book, modern physics, they've somehow taken these Associahedra and they've related them to particle physics. Okay, and this is a hot topic in particle physics nowadays. When you type in Associahedra, you get, I forgot his name, from Princeton. He's a physicist, and he invented these shapes that show how different particles associate with each other. So they also talk about Associahedra, Permutahedra, and now something called a cosmohedra. Somehow they're describing the shape of, not the shape of the cosmos, but the shape of all interactions that cause the cosmos. So, but the very important thing is, these are shapes that describe physical phenomenon. Okay? Google search. It's a little bit beyond my pay grade. I tried to understand it a few times, but it doesn't go that simple. Okay, great. Okay, the last topic, the last thing we talk about is that formula for the Catalan numbers. I don't want to go through the proof. The proof is a little bit technical, but the idea is as follows. The picture is pretty. Okay. So we're talking about parentizations. And these are legal parentizations and illegal parentizations. Okay, and I'm sorry, the proof is, okay, so these are the illegal ones, and they correspond to what's called unbalanced parentizations. Okay, and the way the proof works is as follows. It's very easy to put down, to count all of these big guys, okay? Namely, you're counting how many parentizations are possible easily. And the idea is as follows. You know, you have A, B, C, D, E, F, G. Okay, let's say you have that. So basically you have parentheses, you can put parentheses in n-1 positions. Okay, you can put it here, 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 here. Okay. Okay, but if you don't put it here, then you're going to put it here. So you have n-1. And the question is, do you put open parentheses or closed parentheses? In each one of them, do you put open parentheses or closed parentheses? Open or closed, okay? And so there's very easy to count how many ways you can put those parentheses. It's n-1 positions, choose, I'm sorry, it's, you have 2n minus 1 possibilities, and you choose n of them, something like that. Okay, and basically what you do is that gives you all parentizations, but you're not interested in the illegal parentizations. You're not interested in the ones which don't have opens and close, matching up nicely. So those are the illegals. And it turns out that illegal parentizations correspond to something called unbalanced parentizations. So it's hard to count illegals, but it's much easier to count these. So what we do is we count these unbalanced. And basically the legal ones, here's legal and illegal, is equal to all of them, easy to count, minus the unbalanced, because that's an isomorphism between them. That's the way the proof works. It's a very nice proof. It should be seen once in your lifetime and go through it. And again, this Catalan numbers show up in many different areas in combinatorics about going up steps and things like that. Anyways, but that's very nice. Anyways, chapter 5, chapter 6, and chapter 7 is a lot of discussion of this coherence thing. And it's important, and it shows up everywhere. It's just like algebra shows up in all of math and science. Higher dimensional algebra, coherence theory is going to shows up and will show up in all over. And we'll see more about that. Especially, we'll see chapter 10 when we talk about higher categories, not only objects, morphisms, and natural transformations, but higher things. You have more of a discussion of coherence theory and all that works, and all that stuff. Main point is, there's a question always about how many morphisms between objects and to what extent things are unique and not unique. Okay, there's one part I want to just mention again, explaining this obsession with uniqueness. And it goes as follows. Consider these 3 graphs. Here's one graph. Here's another graph. And here's 3 graphs. Okay? And they're very nice graphs. Okay? But if this is A, B, and C, then I can permute A, B, and C. In other words, think of this graph and use it for some reason, but it would be the same graph if I switched this around and made this B and this A, okay? Or I switched this around and made this C and this B. You can do a lot of switching. In fact, there are 6 3-factorial permutations of this graph that keep it basically the same. Again, graphs don't really, what the names of the vertices are not important, and so you can swap these around and you can still have the same graph, essentially. So that's a notion of symmetry. As opposed to that, this graph, so this has 3 factorial, which is equal to 6 automorphisms, ways of changing it. Automorphisms are isomorphisms that go to itself. This one has 2 automorphisms, okay? Namely, this has no little loops. This has a loop, and this has a loop. So if you wanted to swap these or change these, well, you can change this guy to this guy and this guy to this guy. That's it. You can't change this guy to this guy and you can't change this guy to this guy. So basically, here's one here's one display of this group, of this graph. You can turn it and you can swap these 2. So basically, there are 2, okay, 2 factorial, which is equal to 2 ways of looking at this graph, etc. Okay, but this graph is different because this graph, this vertex has no loops, this vertex has 1 loop, this vertex has 2 little loops on it. Okay, and so if you wanted to swap it, one vertex for the other, you can't. The only vertex that you can swap isomorphically with this is itself. The only vertex that you can swap with this is itself. The only vertex you can swap with this is itself. So there's only one way of doing this. So in some sense, when you're describing a graph and you want to keep things fixed, this has a unique automorphism. These, when you're describing it, you still have haziness in what you're describing. Do you mean this, or do you mean this, or do you mean this, or do you mean this? There's 6 different ways. This, do you mean this, or do you mean this? There's 2 different ways. But this graph, there's no haziness in the definition. So this is at the core of coherence theory, namely, to what extent is the mathematical object that you're describing unique? And the answer is, like we said, this obsession with unique, an isomorphism, with a unique isomorphism between them. This has a unique isomorphism between any two description of this. Okay, so it somehow exists, or it's easier to talk about like that. And that's what coherence theory is all about, trying to get these uniqueness. Okay, have a wonderful day.